let's go over solutions to the exam 1 review. So number 1 has a few limits. First one, limit as x approaches 9 of x squared minus 15x plus 54 over x squared minus 7x minus 18. You try substituting 9, what do you get? You get 81 minus 105. Excuse me, that's not 105, that's 7 times 15. 9 times 15, 135, because it's 150 minus 15, plus 54. 81 and 54 make 135. On the bottom, you get 81, negative 63, negative 18. So you get 0 over 0. Now, right here, we get 0 over 0. We can factor this. And this now equals this limit. Notice it equals another limit, because we haven't taken a limit if all we do is factor. The top, 9 and 6 make 54. 9 and 6 make 15. So negative 9, negative 6 make negative 16, negative 15. Negative 9 times negative 6 gives you 54. And in the bottom, 9 and 2 will make 18. 9 and 2 will make 7. And notice here, we want it to be a negative 7. So we'll need x minus 9 times x plus 2, because negative 9 plus 2 is 7. You can now cancel out the like term. I'm not going to simplify that. I was going to write limit as x approaches 9 of x minus 6 over x plus 2. Let's just do the substitution now. So 3/11ths for this one. So this one we had a 0 over 0, and then we factored it. Next one. Next one. Limit as x approaches negative 7 of 4 minus 3x under a square root minus 5 all over x plus 7. Now again, we hope we can substitute. You substitute negative 7, you get root 4 plus 21. 4 plus 21 is 25. Square root of 25 is 5. Minus 5. So you get 0 in the top, and in the bottom, negative 7 plus 7 also makes 0. So again, we get a 0 over 0. Now, with this 0 over 0, we're going to multiply by 1 so that we can get rid of the square root. And which one are we going to multiply by? Well, we're going to use the difference of squares formula to our advantage. So we're going to multiply by that one, where the only difference is the negative is now a positive. Well, now, we haven't taken a limit yet. What does, well, before writing the numerator, let's just write that denominator, because we're not going to do anything with the denominator yet. The numerator, well, we have the difference of squares, so it's the first thing squared minus the second thing squared. The first thing squared, squared and square cancel. Second thing squared, 25, and we subtract. Now what can we do with this? Well, notice this numerator, the 4 and the negative 25 make a negative 21. And we also have a negative 3x there. Excuse me. So we can factor out a negative 3, and we're left with x plus 7 in the numerator. So let's write that down. Negative 3 over x plus 7 all over. And notice here what I just wrote is not correct because I need a limit. So I'm going to write this, I'll just go down over here. Equals the limit. We haven't taken a limit yet. X goes to negative 7. Negative 3 times x plus 7 all over x plus 7 root 4 minus 3x plus 5. We still haven't done anything with the denominator. But now we have an x plus 7 and an x plus 7. So we can cancel them out. And now when we take the limit, we can just do a direct substitution. Negative 3 over root 4 plus 21 is 25. So we have root 25 plus 5. Root 25 is 5, so you get 3 over 5 plus 5. Negative 3 over 5 plus 5. So negative 3/10 for this one. So in this one, we had a 0 over 0, so we multiplied by a convenient 1. And then did algebra. Next, part C. Limit as x approaches 0 of e to x cubed minus x. Again, we will try substitution. We have limits of composition limits of compositions. You can push the limit inside the function. So here we can do that, and that reduces to a substitution. What happens if we substitute? Well, you get e to the 0 minus 0. E to the 0. Well, e to the 0, e is just a number. So e to the 0 is 1. And I don't know number 4 off the top of my head, so I have to look at my phone. I don't have a printer, so I have to look at these on my phone. Part D. Limit as what? X approaches negative 5 of x plus 4, x plus 6, x minus 3 over x to the 5, x plus 5 to the 4. Now, right here, notice if you do a direct substitution, you will get a number over a 0. This term will give us a 0. No other term will give us a 0. So we have a number over 0. So what we're going to do is look at both sides of negative 5. So let's look at the right of negative 5. X plus 4, x plus 6, x minus 3 over x to the 5, x plus 5 to the 4. And this equals, well, we know on the one side it's going to be an infinity. So all you have to do is find the sign of the infinity. We need numbers slightly to the right of negative 5. So there's negative 5. Numbers to the right of negative 5 are over here. So negative 4.9 type numbers. You put that up here, you get a negative. You put that in x plus 6, you get a positive. You put that in x minus 3, you get a negative. This is taking a negative and making it more negative. Down here for x to the 5th, well, it's going to be a negative number to the 5th. Negative to the 5th is negative. And down here, we have a number to the 4th. So inside the parentheses, we would have what? A positive number on the right of negative 5. It's a positive number to the 4th, so that's positive. And this is going to be an infinity. Which infinity? Well, there are 3 negatives. So on that side, it's negative infinity. And now, we'll check the other side. On the other side, oh, this is negative 5, not 5. On the other side, we want numbers to the left of negative 5. X goes to negative 5 on the left. We need numbers on the left of negative 5, so numbers like negative 5.01 or things like that. Substitute that in x plus 4. That again will be a negative. Substitute that in x plus 6. That will be a positive. X minus 3, that will again be a negative. Negative number to the 5th is still negative, and then something to the 4th is positive, and it's an infinity. There are 3 negatives. 2 of them cancel, and you're left with 1 negative infinity. So we say this limit is negative infinity. And since it's kind of a sentence, let's say, since that limit is negative infinity and that limit is negative infinity. So in this one, we had a number over 0. We checked both sides. We got the same sign on the infinity, so we will say that that limit is negative infinity. Next, part E. What do we have for part E? Limit, as x goes to infinity, of what? 5x squared negative 4 over 1 negative 3x positive 4x squared. So right here, what we're going to do is look at, we have a limit as x goes to infinity of a rational function. We'll look at the largest exponent on the bottom, and we'll use that to simplify this. How will we use it to simplify it? Well, we're again going to multiply by 1. The largest exponent on the bottom is 2. So the 1 that we're going to multiply by is, that's a terrible 2. The 1 we're going to multiply by is 1 over x squared over 1 over x squared, because the largest exponent on the bottom is 2. Now, what's this going to do? Well, let's factor that 1 over x squared in. 5x squared over x squared is 5. Negative 4 over x squared is negative 4 over x squared. 1 over x squared is 1 over x squared. Negative 3x over x squared, one of those x's goes away. 4x squared over x squared. The x squareds cancel. And now, as x goes to infinity, this goes to 0. This goes to 0. This goes to 0. So this limit, we've taken the limit now that we're sending everything to 0, so we don't need to write limits here, is 5 minus 0 over 0 minus 0 plus 4, so a positive 5/4. Part F is another of these limits with a different rational function and a different answer. So what is part F? 7x to the 4, negative 3x cubed, negative 4, all over x cubed, negative 3x squared, positive 1. Well, again, we have a rational function, limit as x goes to infinity. We look at the largest exponent on the bottom. It's 3. And we multiply by 1 in this form. 1 over x cubed over 1 over x cubed. Because the degree of the denominator is 3. Distribute that through. X to the 4th over x cubed. Only 3 of those x's are going to cancel, and you're left with one other x. Negative 3x cubed over x cubed. The x cubes cancel. Negative 4 over x cubed. Nothing cancels. X cubed over itself is 1. That's a negative 3 over... Was there a negative 3 over x in the previous one? Maybe. 3x squared over x cubed. 2 of the x's cancel. 1 over x cubed is 1 over x cubed. Now, as x goes to infinity, what happens here? Well, 7x, let's handle that in a moment. 3 goes to 3. That goes to 0. That goes to 0. That goes to 0. That goes to 1. So what do we have? We've taken a limit in some of the components. We haven't taken a limit in everything, so let's still write limit. We have, what, 7x minus 3 over 1. Well, that's a fraction that just reduces to 7x minus 3. 7x minus 3 is just a line. As x goes to infinity, the line will go off to infinity because it's a positive slope. Or you could say 7 times an infinity is still an infinity, and infinity without 3 is still an infinity. So this limit is infinity. Either a geometric argument for this last part or an algebraic. Now, what was was number 2? Probably a definition of a derivative, because that's usually what I would ask second. Yes, a definition of a derivative. Use the definition of the derivative on this function. Negative 3x. Use the definition of the derivative. And then what do we want? Tangent line at 2 values where it has a horizontal tangent. Okay, maybe I'll remember that so I don't have to look at my phone. Well, the derivative, the only thing we know about the derivative is that it's given by this limit. Limit as h approaches 0 of f of x plus h minus f of x all over h. We got that from using secant lines and letting the secant line approach a tangent line. Not limit as x goes, limit as h goes. I should probably write this one on the next line. Yeah, I'll write this on the next line. Equals limit as h approaches 0. Well, what's f of x plus h? Take an x plus h, replace all x's up here. So you get x plus h squared, negative 3 x plus h. There's f of x plus h. X plus h squared minus 3 x plus h. Replace all x's with x plus h. Minus f of x. Minus all of f of x. So we subtract all of f of x, not just a part of f of x. All over h. And this limit as h goes to 0, you can't substitute here because you'll get a 0 over 0. So what we can do is use some algebra. Do some algebra. X plus h squared, well, you could use Pascal's triangle on x plus h squared with this row. So you'd get 1 x squared h to the 0 plus 2 x to the 1 h to the 1 plus 1 x to the 0 h to the 2. Or you could just remember the difference of squares, not the difference of squares, the, I don't know what this other formula is called. The squaring a binomial formula. That's probably what it's called, something like that. So we have x squared plus 2xh plus h squared. Well, that's just this part. Now we need the negative 3. There's negative 3 on the x. There's also a negative 3 on the h. And then we'll distribute this negative, which makes that a negative x squared plus a 3x. And it's still all over h. We haven't taken a limit yet. This I'm going to have to go up here. That wasn't good board organization. That's okay. So what do we have here? Well, we have an x squared and a negative x squared. So those cancel. We have a 3x and a negative 3x. So those cancel. And what are we left with? Well, we're left with limit. Still haven't taken a limit. As h goes to 0 of 2xh plus h squared and a negative 3h. And this is all over h. Well, we still can't substitute h equals 0 here. Because if you did that, you'd get 0 over 0. But what you can do is notice that all of the pieces of this equation have h's. This one has an h, that has an h, actually it has two h's. That has an h, and that has an h. So you can cancel an h in each term. Cancel an h, you get a fraction over 1, so I'm not going to write the 1 in the denominator. Cancel an h, you have 2x plus 1h and a negative 3. And as h goes to 0, you can now substitute h equals 0. You get 2x plus 0 minus 3. Also known as 2x minus 3. Well, that was just part A. I don't think I wrote a letter A on the board when I did that. Part B said find an equation for the tangent line at x equals 2. Well, equation for a tangent line. We need a point. We need a slope. Well, what's the point? The point was given to you as x equals 2. So now we need a y value, and to get the y value, we need the function that I erased. What was it? X squared minus 3x. It was just x squared minus 3x. X squared minus 3x, well, we need f of 2. F of 2 is what? 4 minus 6, which is negative 2. So we have 2 and negative 2 is our point. Well, the slope, well, all we need to find the slope is the derivative at 2. F prime at 2, well, what's f prime? F prime was 2x minus 3. So it was 2x minus 3. F prime of x, so f prime at 2 is 2 times 2 minus 3, which is 1. Is it 1? Yes, it's 1. So we have our point, we have our slope. So an equation, I'm going to write this above. Well, maybe I'll write it above. So equation for the line tangent, we'll use point slope form. Y minus the y value, so y plus 2 equals 1 times x minus 2. You could leave it like that. I'm just going to get rid of the 1 because I think that looks bad. And I'll leave it like that. Y plus 2 equals x minus 2. You could solve that for the slope-intercept if you want, but you don't have to. You could have left it in that first form if you wanted. Oh, I didn't do part C. Find all x values at which f of x has a horizontal tangent. Well, a horizontal tangent. What does a horizontal tangent even look like? Well, let's draw one. A horizontal tangent. There's a curve of some kind. A horizontal tangent looks like that. Or it looks like that. So we want all the points where the derivative equals 0. Well, in part C, we're given the derivative. Well, we're actually given the derivative in part A, I guess. But in part C, well, all we need to do is set f prime equal to 0 and solve for x. So 2x minus 3 equals 0. Add 3, divide by 2. X equals 3 halves. So at x equals 3 halves, the function has a horizontal tangent. Number 3. Given this function, approximate the area between this function and the x-axis on this interval using 4 rectangles. Well, remember how this works. We're going to set it up so that the base of all the rectangles is the same. The bases of all the rectangles are the same. If we want 4 rectangles on this interval, then all their bases are going to have length a half, because that interval has length 2. But let's draw a little bit of this and then set up the formula. So we want the interval 1 to 3. So let's mark off 1. Let's mark off 3. And we want to divide this piece into 4 pieces. Let's divide it in half. Let's divide it in half again. We have the points between 1 and 2. 1 and 2, midpoint is 3 halves. You could arrive at that many different ways. The way I arrive at it is with money and thinking about money. I think this is a whole dollar, this is 2 whole dollars, so in between them, $1.50. 2 and 3, between that, 5 halves, $2.50. Well, we want 4 rectangles. Well, this question one, both approximations or just one of the approximations? Find an approximation. Okay, so you have to do only one of these approximations. So right now, this function looks like something. This actually isn't what the function looks like. The actual function, I guess, looks like this because it's a parabola. But what it actually looks like doesn't matter for our approximation purposes, unless we're going to interpret them, which we're not. So right here, remember, the one approximation uses these left endpoints, and not this last one. The other approximation uses the right endpoints for the rectangles. So let's do the one on the left, because that's what's drawn there. Remember what we're going to do? We're going to use this point and that function to figure out the height of the rectangle. Notice the base here, each of the bases is 1/2. And the heights are going to be given by the y values associated to these x values. So let's put that all together. We get the left approximation with 4 rectangles is all of the one side length is 1/2, and the other pieces are just the heights of these first 4 rectangles. So that's f of 1 plus f of 3/2 plus f of 2 plus f at 5/2. And similarly, the right approximation, you might want to leave a couple lines between your left and right approximations, because I'm going to simplify that in a moment. The right approximation, instead of using these 4 endpoints, is going to use that endpoint, that endpoint, that endpoint, that endpoint, and the rectangles are going to be formed like this. There's the height, and it goes over. There's the next height, and it goes over. But the bases are still going to be the same. So R4 equals 1/2. Instead of starting at 1, we're going to start at 3/2. 1/2 times f at 3/2 plus f at 2 plus f at 5/2 plus f at the last number, which is 3. And now we'll simplify these. So hopefully you took that advice and left a couple lines of space between L4 and R4. I'm going to continue L4 here. If you left space, you would continue right under. Equals 1/2. F of 1, 9 minus 1 is 8. F of 3/2, 9 minus 3/2 squared is 9 minus 9/4. I'm going to leave it like that. I mean, you could write that as one number. I'm just going to leave that like that. 9 and negative 9/4. You could make it, what, 7 and negative 1/4 if you want. I'll leave it like that. F of 2, 9 minus 4 is 5. F of 5/2, 9 minus 5/2 squared is 9 minus 25/4, and I'm going to leave that like that. And we stop there because that told us to stop at f of 5/2. And what does this equal? Well, let's combine all the whole numbers. 8 and 9 make 17, 5 and 9 make 14, 17 and 14 make 31. Or you could have done, what, 18 and 13. Or something else. And the rest, we have what, negative 9/4, negative 25/4? Well, that's the same as negative 34/4. That's the same as negative 17/2. So we have 31 and negative 17/2. So that's what, 1/2. 31 is 62/2. 62/2, negative 17/2. 62 and negative 17 make 45. 2 and 2 make 4. So L4 gave us 45/4. The directions said you had to do only one. I'm just going to do both in case you chose to do R4. Let's find R4 now. R4, 1/2. F of 3/2, well, we wrote that up here. 9 minus 9/4. F of 2, we wrote that up there also. That's 5. F of 5/2, we wrote that up there. 9 and negative 25/4. I never understood when they taught you mixed numbers why they assumed that the fraction had to be positive. And they could just as easily be negative. 9 and negative 25/4. That sounds perfectly fine. Or actually, what they don't want an improper fraction for that. So it would be 3 and negative 1/4, or 2 and 3/4. Not 3 and negative 1/4. I like that more. Where was I? I got sidetracked. F of 5 halves is there. F of 3, well, F of 3 is convenient because it's just 9 minus 9, which is 0. And now we'll add these numbers together. I'm going to do it the same way by adding the whole numbers first, and that's nice. We can do that. You can add in whatever order you want. 9, 9, and 5 make 23. This is again negative 9/4, negative 25/4, negative 34/4, negative 17 halves. And then what does that equal? 23 is 46 halves. 46 minus 17 is 29. And then there's still a 4 on there, 2 times 2. So we did both of those approximations. You had to do only one based on those directions. And on exam 1, it also says to do only one for the actual computation. Well, it might say, well, it will say that. I haven't completely written it yet. But it will say to do one of the approximations. And you can choose whichever you want. Part B of this question says to set up 2 formulas for the area between the curve and the interval 0, 2 using 5 rectangles. Well, let's draw out this interval. So here's 0, here's 2. Well, we need to divide this into 5 pieces. Well, that's easy enough to do with lines. 5 even pieces. That's not easy enough to do with lines. But let's say that divided it evenly. How can we find this first one? Well, we use the numbers to our advantage. This interval, the whole interval, from 0 to 2 has length 2. That interval equals 2. The length of that interval is 2. We're dividing it into 5 pieces. So each piece is going to have length 2/5. We started 0, so the next one is 2/5. 2/5 and another 2/5 is 4/5. 4/5 and another 2/5, 6/5. 6 and another 2/5, 8/5. That's not a 5, that's a 2. Now it's a 5. So we have all of the x values just by using the length of the interval and dividing it into 5 pieces, starting at 0. Well, now we need the 2 approximations. So L5. The base is 2/5 in each case, so we'll write 2/5. And we'll factor that out. And the heights for the left approximation use the left endpoints. Those endpoints. So we need f of 0 plus f of 2/5 plus f of 4/5 plus f of 6/5 plus f of 8/5. We stop at 8/5 for the left approximation. For the right approximation, instead of using the left endpoints, we're going to use the right endpoints, which are those. The base of these rectangles is still 2/5 in each case. So we have 2/5. Instead, we're going to start at 2/5 and then go to 4/5 and then go to 6/5, 8/5, and the last number, which is 2. And you don't have to simplify those further because it says just set up the formulas. Part 4. Find the real number a which makes this function continuous. Let's write out the function and then deal with that. So f of x equals, it's defined in pieces, 3a cubed negative x squared, x cubed plus 1, and it's 3a cubed negative x squared when x is less than or equal to 4, and it's the other thing when x is larger than 4. So we want to force this function to be continuous everywhere. Well, the first observation is it's just a couple polynomials. So it's continuous on both of those pieces, the open intervals. So f is continuous this is 4 on negative infinity to 4 and 4 to infinity. So all we have to do here is force it to be continuous f4. And we'll do that by checking limits on both sides of 4. So limit as x approaches 4 from the right of this function. Well, on the right, this function is defined as x cubed plus 1. On the right of 4, it's defined as x cubed plus 1. So we have 4 cubed plus 1. 64 plus 1, 65. And what we want to do for this to be continuous is have that be the same as the limit on the left. Limit on the left of 4, well, on the left of 4 the function is defined 3a cubed negative x squared. A lot of cars driving by it. I wonder, can you actually hear those cars? A lot more cars driving by than usual. Where was I? On the left of 4, the function is defined up here. So we have 3a cubed. There are no x's there, so we're not going to substitute there. But it's negative x squared, negative 4 squared. Negative 4 squared is negative 16. So this function will be continuous at 4 when these values are the same. So we'll set them equal. 3a cubed negative 16 equals 65. 65 and 16 make 81. 81 and 3 make 27. Cube root of 27. Cube root of 27 is 3. So a equals 3 makes f continuous at 4. I'll just write it like that. So right there we had to force the limits on both sides to be the same. Both sides of 4 in this case. Next one, number 5. Sketch a graph of cosine x. So here's a graph of cosine x. Let's label some of the points. That's a terrible labeling. Up here, remember cosine x. Remember cosine x goes up to 1. Cosine x goes down to negative 1. You don't have to write your two ones the same. It starts repeating itself after 2 pi, and then the rest is divided up by pi over 2 and 3 pi over 2. Those are the relevant points. And then similarly over here. Part B says, I forget what part B says, something about the inverse. Does f inverse exist on the domain of f of x? No. Why not? Well, for the inverse to exist, we need it to pass the horizontal line test. No. F of x equals cosine x fails the horizontal line test. And then part B says restrict the domain so that f inverse exists. There are many answers for part C. You could say, if you wanted to say it based on what the instruction said, you could have said, you could have restricted the domain to just pi. But what I will do, is restrict the domain so that it hits everything between 1 and negative 1. And here, to get all this, notice that's that piece, it satisfies the horizontal line test. So The inverse will exist on that interval, and this interval is what? It's 0 to pi, and we're going to include the endpoints. That's not a three-tailed pi, that is a dashed line. There. Part 6, number 6. Solve for x. Solve for x. Log base 2 of x plus 1, negative 2 log base 2 of x minus 3 equals 1. Well, let's first combine those logs. They have the same base. Well, actually, let's first get rid of the 2 before combining. You could have done this in one step. But first, I'm going to put that 2 on the x minus 3, because that is a property of logarithms. Multiplication becomes an exponent. Still equals 1. And now we have a subtraction, so we can combine these on the left using division. Still equals 1. We haven't done anything to the right side. So these are subtracted logs with the same base. So it's this thing, log of this thing, divided by that thing. Well, now, to get rid of the log, how would we solve this equation? It's supposed to be an equal sign. 2x equals 5. How would we solve that? How would we solve 2x for x? How would we solve it for 5? Well, it's already solved for 5. How would we solve it for x? Well, we'd get rid of that 2. How do we get rid of the 2? By inverting it, or multiplying by a half, or dividing by 2. All of them are the same. How do we get rid of a log? We invert it by using an exponential. Remember, the logarithm is the inverse of the exponential. So we can do 2 to this side equals 2 to this side. I'm not going to write that out like that, but that's the math. We're doing 2 to this side. Well, the log cancels. 2 to the other side is 2 to the 1, which is 2. And now we have to solve this equation. Well, let's get rid of the fraction first. So multiply both sides by the denominator. The left side is just x plus 1. The right side is now 2x minus 3 squared. Now we'll solve this for x. Square that thing on the other side. X plus 1 equals 2. X squared, negative 6x, positive 9. Distribute the 2. 2x squared, negative 12x, positive 18. Put all the like terms together. I'm going to put, I like when this number is positive, so I'm going to put these x and the 1 on that side. Negative x and negative 12x make a negative 13. 18 and a negative 1 make a 17. We removed everything from one side, so it's now set equal to 0. You could try factoring that. Won't factor. Doesn't look like it factors. So we'll use quadratic formula. The directions didn't say we couldn't use quadratic formula. What's quadratic formula? B squared that. Quadratic formula. Negative b, negative 13 is positive 13, plus or minus square root of b squared, 13 squared, 169, minus 4ac. 4ac is 8 times 17. 17 times 10, 170. 17 times 2, 34. 170 minus 34, 136. So we have b squared, negative 4ac, all over 2a. 2a is 4, and we'll combine them and hope we don't have to do any more simplification, because I don't like simplifying square roots. Yeah, we don't, because that's just a 23. Oh no, that's 33. 33. So we have these numbers, but remember what the original function was. The original function was log of x minus 3. There was a log of x minus 3. So we're not going to be able to take the positive one, because the domain of a logarithm, remember, is 0 to infinity. So we need that here, and here, that means all we'll take is the positive of these two, because the other one is going to be forced negative by the x minus 3. Don't worry too much about that. Just take the positive. That'll be how I set them up to work out. So if you have any questions on this review, let me know. The test will be similar in that there will be limits, definition of derivative, approximation of the area, probably one of those continuous questions. So let me know if you have any questions.